So, if you think about, I suppose if you think about initial conditions, our next speaker is one of the initial conditions that led to me coming to Norway 8, 9 years ago. I don't remember now. And he's going to talk about, something completely different. So in the kind of like theme of the conference, there's all sorts of different ways of thinking about these things. And so I invited Danny, who's Danny Caballero, whose background is in both applying AI to education research topics within education itself at the university level, and I think also high schools. But also he has worked in how do students learn about physics through computing to begin with. So he is my former PhD advisor, which is why I can give a much better introduction than I did for any of the rest of you. I'm very sorry. But thank you for coming to Norway and giving your talk so far. Anyways, I'll stop talking and I'll let Danny take the floor. So we have Danny next, and there will be one more speaker. And please, 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 there is a discussion zone after the last speaker. Please take advantage of that, but please do not forget there are plenty of people who've come here to present posters. They're on the other side behind the stairs, and that will start at 4:30. Yeah, so I'm done.
Thanks, John. Hi, folks. Y'all can hear me all right? Yeah, awesome. Well, I'll apologize ahead of time for, I guess, John's career in bringing all of you here, I suppose. But I hope that you enjoy this. I'm going to tell you a little bit about science education, and I have a little correction to the talk title. This is not John's fault. This is my fault. I want to argue that we need more science education research when we're thinking about AI in science spaces. So I'm going to start with just why is this science educator at your AI conference? You can blame John for that. I'm currently a professor of physics and computational science at Michigan State. I co-direct 2 research labs. They're both focused on education, one in physics, one in computational science. I have a PhD in physics. I did a postdoc in physics education. I'm a former high school physics teacher in Atlanta. I'm a current labor organizer for our union faculty at MSU, and I've taught there for 12 years. And these are just pictures of my kids, my family at Halloween, and my official photo. So why do I think John invited me? I don't think it was just to catch up. There's some things that I'm going to share with you today and sort of give you some context for this. So I've been a part of 3 massive research efforts in science education, including one here in CCSC over in the physics department. I've worked on a decade-long national effort to integrate computing in the United States in physics courses, and I've been helping bring computing across the physics program at MSU into our area high schools. I think one of the reasons I'm here is I like helping people think about and solve big problems in science education, and I think that AI is one that we want to be thinking about. Because the question that I think we are all trying to figure out is what's the relationship between education and science and artificial intelligence, right? So this isn't a presentation that's going to tell you how to do this stuff. If you want, you can just ask ChatGPT how to use it in classes, and it'll tell you. This is about framing the issue longer term and trying to understand it a little bit bigger than that, okay? So artificial intelligence has arrived, and it will disrupt education. You can add those words together and put them into Google, and you'll get several articles, including this one with a DALL-E 3 created image of what it might look like when our new AI overlords are teaching in classes. But really, when you read these things really carefully and you try to understand what people are talking about, they're talking about benefits that are potentially very, very good, things that we really do want. More personalized learning, greater support for teachers, especially reducing their administrative burden. In the United States, most teachers are working 50, 55 hours a week, and a lot of that work is administrative work. It's substantial. Thinking about enhancing student engagement so there's more participation both in class and out of class. Thinking about analytical tools that can help us address issues of learning potentially earlier on. Expanding access to education. This is particularly important in the United States where we have a bunch of folks in rural communities, but we also have folks in urban communities that don't have the same access that students in suburban and wealthier districts have. Supporting students with different needs, whether those are learning disabilities or other sorts of issues that we want to accommodate. And then helping with collaboration and so forth, right? These are all things that potentially artificial intelligence can help with. But there's numerous concerns about this, right? There's issues of automating inequity due to algorithmic bias, taking humans out of education and dehumanizing the process of building our society. Issues of academic integrity, having concerns about privacy and data security, particularly when it comes to student records. We have a federal law in the United States that protects student records very strongly. I'm sure that's true in other countries as well. One of the major concerns that we have is deprofessionalizing the teaching of students and losing teaching jobs, right? Taking teachers out of the equation, being overly reliant on technology for that work, and also issues of ethics and transparency. But I want to frame this issue because it's not just about sort of benefits and concerns, right? It's about sort of how we think about approaching this. So there's a few different frames I want to share with you. The first one is technological solutionism. This is the idea that tech can provide the necessary solutions to solve problems, right? So this will help with things like issues of scale, which are really important in the US, where we have more and more students, going into schools, but more and more students going into university education than ever before. We have to address issues of funding. People talk about issues of efficiency, being efficient in these educational spaces, making sure that people move on to the next space, emphasizing this idea of personalization, and really taking advantage of new technology. And I put some lists of some folks that have talked about this in different ways. Sal Khan, Sugata Mitra, who did the hole-in-the-wall computing experiment in India, Daphne Kohler, former DC Chancellor Michelle Rhee, right? These are all people who think about this in a very sort of economic, nuts and bolts kind of way. Another way to think about this is human-centered education, right? Where social relationships, the relationships that we have with each other and with other people in our community are really important. And those instead emphasize the concepts of critical thinking. They leverage experiential learning. They promote socio-emotional development, right? And they center humans in tech. This is probably the experience that many of us had in our own education. This is where we're kind of how we were taught. And that's probably because of John Dewey, who is one of the sort of most senior educational philosophers that is out there, right? This man talked about experiential learning before it was a thing. But there's other folks too, including Seymour Papert and Andy DeSessa, who are really strong technologists who centered humans in their work with computing education. And then y'all probably have heard of Pasi Salzberg, who's in Finland. Third frame, and it's an increasingly, I think, important frame, is education as a tool for justice, right? And this frames education as a political act of liberation. It's meant to promote diversity and equity across all of these different systems. It's meant to emphasize social justice and liberation, and it recognizes the fact that educational systems, as they exist, perpetuate inequities. And these are folks like Paulo Freire, Bell Hooks, Henry Giroux, Ruha Benjamin, and so on. Right? So we can think of these three frames as being potentially useful for us at different times depending on the context. So I just want to make sure that we understand that these are different ways of thinking. They're not necessarily in tension or in competition. They're just different ways of thinking. Now, one of the major issues that we've run into with this work is that there's been just rapid development. The development of these tools is just too quick for education research capacity and space. This is just some figure that I picked up for how ChatGPT has developed over time. And when it became public with GPT-3 to GPT-4, only 3 or 4 years have passed, right? And we've seen some incredible capacity for using that tool in different ways. But if you map this change onto how we see changes happen in science education, the timescales just don't match. The timescales for change are decadal in science education. This is work by a colleague of mine, Tor Odin, who's here at UIO, where he used natural language processing to characterize the publications in science education. And what you see are these sort of hills and valleys, these rises and falls, but they're on the order of like 20 years. Right? So this one here is when we changed the way that we do teacher preparation in the United States, there was a whole different approach to doing it, and that took 20 years to be taken up into the field kind of fully. And so when we're thinking about the ways that we're making changes to education, right, the technology just simply outpaces the ability of researchers and educators to implement it with real effect, right? So we do have to be concerned and talk about these things. The other thing is there's a pretty significant complexity to the work that we do in education research. This is sort of a pathway of a student that's maybe going towards a STEM profession, right? So they start off in elementary school, they go to middle school, they go to high school, they may go to what we call in the United States a two-year college. It grants a two-year associate's degree. And then they may go off to a university to earn a 4-year degree. They may go to grad school, and then they'll go into a position. And there's also feedback in this system, right? The folks that are going into those jobs are often coming back into these educational spaces as educators or administrators or what have you, right? And so the space in which we do our research, my group does our research, is in this space with the sort of relative sizes indicating how much research we do in those spaces, mostly in high school and university, a little bit of grad education. I won't talk about our 2-year college work. But the thing that I really want us to consider, and this is, I think, why we're all here, well, not why we're all here, it's why I'm here, because it's big brain time. What is this relationship that we should have, right? How should we think about this? And what I would argue is that we need to do education research that influences classroom instruction, and that classroom instruction should feed back into our education research. So what I'm going to use as my example, because we again, it takes us a long time to do this work. I'm going to use the example of computing in physics education, which is what we've worked on for a long time, and then we'll talk a little bit about AI. So this stems from, I think we can all agree, computing is just how science gets done, right? There's a metaphor here with 3 legs to the stool of supporting the work of science. With theory, experiment, and computing, and they certainly blend together in different ways and so forth, but it's essential to what scientists are doing. And way back, we did some work on this at Georgia Tech, where we were studying introductory students learning how to write Python code for the first time in physics courses. And what we argued in that is that computing in physics was using the computer as a tool to model, to simulate, and visualize a physical problem. That was our definition of it. And what we did was we trained students through their homework examples to solve physics problems with Python, to make models of different systems and to model the dynamics of it very, very quite simply. And you can see some of the simple code that we've provided to students and that they worked on. And we wanted to just categorize their mistakes and try to figure out what's going on here, right? So this is very early work where we don't have much of a strong definition for what we think this is, and we're just trying to figure out, well, what can people do? This was back in 2012. Since that time, we've been working on some other theoretical developments. This is work that I've done with Tor here at UIO and my colleague Elise Lockwood, who's at Oregon State, where we began to develop a theory for literacy, a theory for understanding computing in the space of physics. What does it mean to do that? And I don't have a ton of time to unpack this, but it's a blending of the practices, the things that people do, the knowledge that they hold, and the beliefs that they share in both physics and computing, and that there's some overlap between those two when you're engaged in physics computations, but also that there's a social dimension to it, that there's some aspect that involves you conversing and discussing in a community around your, coding and programming and simulations and so forth. What's really nice about this work, and Tor's just actually finished some more work with our colleague Ben Zwickle, was that this is actually a model that we can use to inform activity development and pedagogy. So if we look for certain things that we want to see happen, that is, we're in a classroom and we see students learning how to do certain kinds of computing, certain kinds of discussion around that computing and building those practices in, how does that actually manifest itself in the activities that we have? And so I'm not going to unpack all of this, but the idea is that now we have a real framework to be able to understand what is it that students are doing and how does that influence the outcomes that we see, right? And I want to point out, there's been 12 years between this paper and the first one that I showed you, right? So we're talking about these sort of decadal levels work, right? It just takes us a long time to come up with these ideas, build them up, and sort of build them to a point where we can make sense of it. So that story really starts with work on just figuring out who was teaching computing at the time. So we did this study across the United States to figure out who are these folks that are teaching computing and where are they teaching it in? And we gave them a survey. We found that roughly 50% of departments across the U.S. with some random sample of those departments said that they were teaching computing. There was no difference between intro and advanced courses. But what we did find was that there wasn't a lot of opportunity for students to work interactively or work together on these things, and there wasn't a lot of assessment work. Now, what was interesting for us about this was we actually tried to figure out, well, who is actually responding to this survey, right? This seems like a really high number when we go out and we go to physics departments. People aren't, teaching computing at this point. And we were able to figure out that actually the sample was quite biased towards enthusiastic educators, right? So you get an email in your inbox that says, hey, here's a survey on computing, right? Who responds to it? People that are interested in computing, right? So fair enough. But the point is, it wasn't a very diverse group, and so what we started to do was launch an effort on faculty professional development. So here's a big picture of us the last time we were all together. So there's a group of about 75 faculty from across the United States learning how to integrate computing into their physics and astronomy courses at this workshop we run in River Falls, Wisconsin. The National Science Foundation funded this for 5 years, and they've just funded it again for another 4 years. So we're going to keep expanding the scope of this. Those folks are participating in a group called Pickup, the Partnership for the Integration of Computing in Undergraduate Physics. This is where they're all from, at least at some point in time. This is a pretty old figure now. But the kinds of things that folks do in that space is they build up activities that they can then share with other people. So one of the key components of this is open source materials that can be used by other educators and that are documented really, really well. So here's my colleague Ernie Behringer at Eastern Michigan made this activity for his mechanics course, and then built this up so that it could be shared with everybody. It has learning objectives, it has some details about the assignment itself, but if you dig into this, it actually has solutions, it has helpful exercises, activities, et cetera, extensions, and so on. And there's many, many of these such activities at this website if you're interested. So you can build this sort of program and sort of start teaching people how to do this stuff, but then you have to acknowledge that this is still a very complicated problem because we're working in these colleges and universities, and then we're working inside of a physics department, and you have a course that you're actually teaching, you have a meeting for your class that's happening in a particular kind of room, you have an activity that you want to engage students with, and then you have maybe a specific task that you're actually asking them to do, right? And the concept of research applies to all of these frames of context, right? We've done research in all of these different spaces at different times because they all interact with each other. And if you're going to do this full effort of integrating computing, it touches all of these different things, right? So one of the courses that we've designed for about the last 10 years is an introductory physics course with computing called Projects and Practices in Physics. This is taught in a group-based format. Here's some students here working around a table with one computer, and they're working on problems that are literally just this. They're written exactly like this. So this is the first problem is one that they would do on a Tuesday, and the other one they would do on a Thursday, and that's all that they would do for 2 hours. These activities, some of them are analytical, but as you can see, this one here is computing related. So we give students a program that runs, but it just runs without error. It actually doesn't model the appropriate system. And so they're spending their time discussing with each other the physics that they know and then putting that physics in Python code appropriately to construct this model, right? They do this, I think, roughly 8 times a semester out of like 30 class meetings. And we have another course as well. The E&M course does it very similarly. So this kind of structure and design is able to support students who have no understanding of computing to start with to be able to do some computing. We don't expect them to have any computing coming in. They often do not. The other thing that we've done is we've expanded that work across our entire department. So I'm going to just sort of highlight a few things here. So this is typically what a student would go through our physics major from top to bottom. Those are the courses that they would take. The green colors are telling you that there's computing that has been integrated into it, typically with Python. And we've gotten to the point where after, again, almost 10 years, right, that we have integrated computing into almost all of our majors courses with some regularity, right? They're coming into these courses and they're learning how to do computing in that part of the major, whether that's E&M or quantum mechanics or well, StatMech has been a hard one for us to get into, but we'll figure that out. But again, long time scale and a lot of sort of work around that. As we see like other organizations interested in this, you start to see them start making statements about what kinds of things people should learn in these spaces, right? So computing has been a big part of physics for a long time. It's only been a big part of physics education for maybe the last 15 or 20 years. But now you have national organizations like the American Association of Physics Teachers telling folks what maybe should be in courses. You have conferences like ours that we had where we're planning for the next decade on how to define learning goals, how to develop assessments, how to help departments do integration, how to expand the number of faculty, and so on. And then you have the APS saying to be a good physics department, you should be teaching computing, and they've given you a guide, which they've cribbed a lot from our work and our research, which is fine. But it's there, right? It tells you sort of what kinds of things you would want to do to get into that work, right? And further, acknowledging that this is not just an issue at the university level, but it's also an issue at the K-12 level, right? So this is something that we have to think about going a little bit back into the educational system, right? And we can talk about what it might look like for science courses in our high schools and in our middle schools to have computing in them. And so I was part of this project here where we laid out a variety of recommendations, emphasizing the values within the discipline, recognizing the need for computing across these different sciences, recognizing the importance of diversity, equity, and inclusion, making sure that teachers have proper professional development support, and that research is really needed. It's really critical for us to do this kind of research. I've been a part of that work in high schools myself with this project called Integrating Computing in Science Across the Mitten. The Mitten is the name for Michigan, at least the Lower Peninsula. As you can see in that picture over there, it looks just like your hand. So in Michigan, we have science standards that involve a computational modeling, right? They're very clear about that. Students should be able to create computational models to calculate computational representations to support explanations, and so on and so on. The states love to do this, where they decree these are the things that folks need to learn, and then they provide no support for teachers to actually do that work. And in particular, when it comes to teachers in the sciences, they haven't done any computing themselves, typically, right? They got their teaching degree 10, 20, 30 years ago, right? And it was certainly not prevalent as it is now. And so we designed a workshop for those teachers, those high school teachers in Michigan, to come to Michigan State and to work with us, to introduce computing, to really understand what their courses look like, what they're trying to do with those courses, and help them to develop materials that fit within their course that they're comfortable with teaching. We tried to grow some community across these folks. This is like the last picture of them all together. And focusing on equity. That was a key component of it, because one of the real challenges that we start to see in these courses is that marginalized folks, people who don't usually get to participate in science in the United States, continue to be marginalized, or even are more marginalized when you bring computing in. We don't want to do that. We want to make sure that everybody's a part of this. And so we addressed problems of practice with them when they came back to MSU. We debriefed them on how things were going. We actually recorded their classrooms, and we raised interactions that they were having that were racist or sexist, and had a conversation with them about how that was going and why they made those pedagogical moves. These are hard conversations to have with teachers, especially predominantly white teachers, about how they're talking to their students. But it's important, it's critical. One of the really great things about this is the teachers made lots and lots of materials, and they're available. They're tagged with all of the Michigan science standards. This is a particularly great one because it fit really well with the teachers' existing marshmallow launch activity, where they were building and designing so they could test and prototype, and then the teacher could give them some list of materials that they were able to sort of design their marshmallow launcher with, and this really helped them do that prototyping a lot more efficiently, right? Instead of trying to do all these calculations, they could work on their model, make some changes to it, and then go to the teacher and say, well, these are the materials we need to do this. It's also a research lab. This was a space that we did a lot of research in. There's some work that we did on student perspectives of computing challenges. We have a whole framework for understanding how this is happening in classrooms, what kinds of activities students are actually engaged in. And then a lot of work around race and inequity, because of the classrooms we had were more diverse than the teachers, let's say. So all of this work, I just kind of want to wrap it all up, right, with this idea that there are some seemingly necessary but not sufficient conditions for making this kind of change, right? The effort to integrate computing and physics was done with a variety of activities here, right? We had to define the goals and scope collectively. That involves everybody that's involved in the conversation, whatever that context might be. You have to develop professional development and community around that to support people in making those changes. One of the key factors is respecting the institutional differences and the diversity. The resources that we have at Michigan State are not the same at Central Michigan. They're not the same as UIO, right? We have to understand those differences. Further, we have to acknowledge the complexity of the problem. This involves lots of people. Humans are necessarily messy. It is a difficult thing to get humans to do the kinds of things that you think are important for them to do for whatever reason, right? So this is important to build those relationships. Collecting data on those experiences, tracking your progress, these are important things, and then sharing those successful cases openly. And I would argue that this has to happen if we're thinking about AI in disciplinary context, because the way that people use computing or the way that they think about artificial intelligence or machine learning, it's different in different contexts, and that's okay. We can respect that. But it also needs the work of scientists, educators, and education researchers. We have to work together, because there are things that are at the limit of my knowledge in terms of artificial intelligence and machine learning. There are things I never want to know about it. But I can also help you with designing a course, right? So we have a give and take here. The reason that this is really important to me now is because I'm in this department of computational science. This is the Computational Math Science and Engineering program. And you can maybe see a very similar definition to computational science as you saw to computing and physics. This comes from my former department chair, which is how well we have this department defined. We use computers to analyze and solve scientific and engineering problems. Computer science focuses on the science of computing, and CMSE focuses on computing to do science. And if that's not clear, there's a three-ring circus sitting right there that tells you where you should be. And so it involves disciplinary modeling, computer science, and mathematics approximation theory all together, right? But for me, the important thing is that we are a bachelor's granting, master's granting, and a PhD granting department, right? And so we have a bachelor's program in data science and computational science, and so we're teaching students to do this, right? We teach computational and data science in these courses to many, many students. So here on the left, you see a bunch of students working together. They're all working on activities like the one over here on the right, which is a numerical integration problem that we have in one of our introductory courses. We use Jupyter notebooks in pretty much all of the work that we do. That's just a standard for us as a department for the most part. There are some courses that we teach in C, there's some that we teach in R, but for the most part, our courses are taught with Jupyter notebooks and Python. And students do a variety of things. From machine learning and classification to looking at different forms of data and trying to model those data. This up here is actually a plot from a course that I taught in statistics where they were looking at, I think it's NBA players or maybe it's football players, and trying to understand the different player positions and how those relate to different measures of their ability to run and their weight and stuff. And also issues of ethics, right? So this assignment up here at the top is about ethics and how you understand ethics with respect to machine learning and data science. Just to dive in just a little bit, right? Our introductory course in computational science is called CMSE 201. It's for any STEM major, any science or engineering major can take it as long as they've taken Calculus 1. These are the goals, which I think they seem reasonable, right? Gaining insight into physical, biological, and social systems, writing programs to solve common problems, et cetera, et cetera. This is sort of the standard fare for us right now. We have an integrated approach to that instruction. So that instruction always blends modeling, context, and programming together. So students are always working to solve different kinds of problems in context where the relevant algorithms or approaches are actually useful, right? So we actually just did this activity right before I left for Oslo, where we were visualizing data and the students were looking at the Great Lakes levels and then looking at correlations between those water measurements to understand actually how the physical relationship of the Great Lakes gives rise to those stronger correlations. So again, this is early stuff, right? But it's important. For now, our department has two major concerns when it comes to AI. The first is the use of AI in CMSE classrooms, and I've given a couple prompts here, things that seem reasonable. I'm taking an introductory computational science course. Can you give me 3 example questions for using functions for plotting? Right? This is something that my students might ask in a classroom as they're preparing for their exam or quiz or something to get some extra examples. Or I'm confused about variable scope. Can you provide a working and non-working example? Right? And these kinds of tools can be used in this way to really help support students. They can be used in other ways, which I haven't shown here, that don't support student learning. On the other side, we have a responsibility to the students that we're educating in machine learning and in data science to recognize that they're in a world that's going to have this stuff, and that world has issues with respect to the use cases, right? There are ethical issues with some use cases. There are ways of thinking about AI and machine learning that are problematic for society, and we want to raise those issues to them so that they can understand that they're going into a world that's not simple, it's complicated, and the skills that they have are useful, but they also have to make judgments about how they want to use them. So I have some examples here, right? Of course, we have some neural network, and then there's some books that we have as part of our seminar courses that we teach. And also, if you're interested, this paper here, Racial Justice Amidst the Dangers of Computing Creep, is a very good one. Excuse me. It's a dialogue between my colleagues Niril and Aman, who actually don't agree with each other at all. And then they resolve to agree with each other on some points at the end of it. It's a conversation. It's written in the style of sort of a bell hooks article, which is really great. Okay, coming back to sort of the AI bit here, right? I want to bring this back up again and remind us that like there's no single frame that is exclusively used in practice. All of these frames have value in different contexts, and we have to sort of think about where we're going to sit with these frames when we're designing these activities. But to answer this question, what's the relationship between education and science and artificial intelligence? I think we need just a lot more research. We have some really big questions to start, and we're working on some of that stuff, and I'm happy to talk with you all about it later. But things like how do students develop an understanding and relationship with AI in science classrooms? In what ways are they using it productively or unproductively? How does teaching students science change when the AI can write nearly all the code that they would use or write themselves, right? What is the sort of purpose of that tool? How do we engage students in discussions about AI ethics and justice, right? How do we do that in a way that allows them to make decisions about that relationship for themselves? How does AI exacerbate or mitigate inequities that we see in these classrooms and in science learning, right? We don't have answers to that. And how do we engage a broader cross-section of scientists to do this work with us, right? Because, again, there's expertise in a certain area, but we need people to participate with us and engage in discussions about this in sort of a larger context. So finally, I'll just end with, I think it's important that we engage in with AI and science education. It will require an authentic and a collective effort to do so. It's essential that we design for AI in science classrooms, because if we don't do it, corporate interests will do it, and they will push it on us, and they will push it on students, and they will push it on families. But also, the future of science demands that we do, because we need people to understand AI in a much broader context than they currently do. And I think it's going to be a lot of work, but I think it's also going to be tons of fun. So I'm excited to work on it. All right, and I pushed this too quickly. So thank you. I just want to show a picture of all the folks that I get to work with every day. And do you have any questions?
Who has questions for Danny?
So you mentioned that when you were tracking the degree to which folks who have more of an issue with access are being represented in K-12 instruction, when you introduced these computational methods, that the discrimination actually got sort of worse, or
It can get worse.
or was emphasized. And I wonder why that is. And I'm asking in general, but I'm also asking because there are some in certain fields, like in the geosciences, who have the hope, including myself, that by us emphasizing the computational side of things, we're actually drawing from communities that are not classically involved in the geosciences, right? Where you have to have some cash to buy a backpack to go camping, which is sort of, So we're hoping to use computational stuff to broaden participation and make the group more diverse.
Yeah.
So the question
the question is, Thorsten?
is that a reasonable hope?
Yeah.
And what can we do for that to actually work rather than backfire?
No, I think that's a really good question, and I appreciate it. I think the framing of hope is not the one that will work, right? It's planning. How are you going to plan for those new people to be in the space and be included, right? And that's a lot of the issues that we see when it comes to teaching, right? Is people express their implicit biases, right? They have gotten in a certain way of doing their instruction, and it doesn't necessarily mean that like people are being actively excluded, but like the experience of students is often, not public, right? They don't tell you publicly sort of why they're engaging in certain kinds of ways, right? And what we see in our work is that, many times the same students, and what I mean by that are the same students that are from marginalized communities in the United States, right? They are not participating or engaging deeply in that work because of their prior experiences of being either shut down or feeling that they're dumb or not feeling that they've been supported. There's many different things we can go into, right? And so a teacher has to plan for that, right? They have to plan for it not only when they're teaching science, but when they bring computing in, because it exacerbates it, because I already don't know how to do this, and now you're adding more, right? I don't know how to do that either. And so I think we can have a hope to have these things happen, but we really got to plan for the people we want to invite to be a part of it. And if we do that, then it works out quite well, actually. We've seen teachers do really good work on themselves to understand how they are, sort of unconsciously causing these issues. But it takes work. It takes a lot of internal reflection and work.
Are there more questions? Yes.
How do you measure success when you design a new class or a new program?
Thank you for that question. Yeah. Again, we only had a little bit of time, but there's a lot of different ways we can do it. We have assessments that help us understand semester to semester whether students are reaching the learning goals we expect, and we look for improvement on that. Obviously, we look for improvement on that with particular groups of students. We do survey students periodically about other aspects, not just learning. But then there's other parts of it, not just the learning part. Like, does this thing run, and can it be run, right? Like, when you make these big changes, you're talking about, like, in particular, let me go back real quick. This course that I was showing you, this course is now taught to something like 600 students in 8 sections of the course, right? So not just success in the individual classroom, but also the coordination and the work to actually build the course so that it runs with fidelity across many sections, right? That's a measure of success also. So we look across these courses for the ways that instructors are doing their work. We do peer evaluations of teaching, so we actually go into the classrooms and we observe our educators and we try to help them get better at the job. So like there's a lot of different, when you say success, it's many, many, many different things, and it's a multimodal sort of issue.
Okay, thank you.
Thank you.
Are there more questions for Danny? So I have a question for you. One is, you mentioned in the middle of your talk about communities of practice. And one thing that I think informed me in learning about, from learning about communities of practice, which I'm not an expert on this, but I guess the basic idea, and please correct me if I'm wrong, is that a practice is something like physics or computing, and there's a community of people who discuss this. And to join that community, whether you become a software developer or a data scientist or a physicist or whatever, you have to learn all the ways that community interacts with it. And that's something that I think about a lot now, advising students or interacting with colleagues. And so one thing is, how do you create that in this kind of undergraduate space? I mean, maybe not in K-12, but like, how does that happen, and how do you bring that back into it? And do you explicitly teach that to students? Like, you're joining this community. That's you're making a conscious choice to do that, getting a degree in physics or computing or whatever.
I think that's a good question. So what John's talking about is, right, sort of an educational theory that suggests that, like, if you are going to be a computational physicist, you have to begin to engage in the kinds of things that computational physicists do, right? And you engage with them more deeply over time, and you sort of understand and what's called reify, like you make your own those practices, right? And I would go actually to our learning goals. Actually, you know what's better is this thing. Golly, sorry. I don't ever use a Windows machine, so I'm just going to do this like a klutz. There we go, is actually this part here, right? The fact that we have sort of framed the activities from the perspective of, like, this is a real thing that you need to be able to do, right? This is something, like, even though it's just maybe just plotting, right? It is something that you need to be able to do. It's done in a rich context. It's not sort of dressed up as some toy thing, right? It's like real data, right? So in part, a lot of it is the way that you do the design from the perspective of, like, let's start from a real project, a real activity. Let's treat it as a real thing. But I think also is the fact that we do it in groups, right? So there's this negotiation process across students, and they're guided by the instructors. They're not, told what to do directly, right? The other thing is that most of these problems don't have a single solution, right? They have like an interpretation of some results, and so that work is validated by other students when they share it out. So we try to model the behavior, if you will, of like the scientific process in those classes, right? Where students are engaged in all those different parts while they're learning the science.
Are there more questions? Thanks, Danny.
Yeah, no worries. It's a great question, thanks.
Then I think we should thank Danny for his talk.
Thank y'all.